Today we're going to talk about how to properly integrate a Hibernian battery system with a thermal management system and walk through some of the fundamentals of fluid, flow and pressure drop to give you the best optimized system for your application. So let's look at a very basic battery thermal management system, starting with the battery pack. The objective of thermal management is to get heat out of the battery pack, and what we're doing is flowing coolant into the pack, out the other side, and through some form of heat exchanger. So for example, the battery packs behind me here have two ports on them, coolant in and coolant out. The objective of this system is to put a pump in a loop that basically flows coolant through the battery, around in a loop, and goes through a heat exchanger, and then back to the pump. This heat exchanger is what extracts the heat out of the battery pack, or in some cases might put heat into the battery pack if it's heating up the battery. There's a lot of different considerations for how you implement your battery pack thermal management system, and real systems can be a lot more complex than this. So we're going to talk through some of the fundamentals and considerations that you need to watch out for. Let's start first with a pump. So all pumps have a very basic function. They move water or a liquid from one point to another. And the way they achieve that is they develop high pressure on one side of the pump and low pressure on the other side. Basically, they push water out one side of the pump and they suck water in the other side. So we're going to look at the characteristic curve of any pump, or a typical centrifugal pump that's in a battery system. We've got the shut-off head pressure here and then the flow rate here. What this curve tells us is basically when the pump back pressure is at a maximum, flow is at a minimum. So basically when you block off the pump or have as much constrictions as possible on this loop and many devices, the back pressure fighting the flow of water will be at a maximum and flow will be at a minimum. So what you're trying to do is to not have obstructions or back pressure or things obstructing that flow in your loop, and you want to develop the highest flow that you possibly can. When it comes to heat transfer, the most important thing is flow rate. Pressure is totally irrelevant. It doesn't matter if the pressure is 1 bar, 1,000 bar, 1,000,000 bar. It has no impact on that heat transfer. It's all about flow rate. So in good battery pack cooling system designs, you're trying to minimize the pressure drop in the thermal management system and the loop. So you want to make sure that you have a battery pack with a low pressure drop, which means that you can use a small pump to develop a large flow rate across the system. So when we look at our pump curve here, in all real systems, there's going to be some amount of pressure drop or head pressure that you have to overcome to develop a flow through a system. And what that means is, once we add real components into this system, it's going to push us somewhere down this curve. So when we come back, you're going to develop only a certain amount of flow rate for that given system. And our goal is to develop as high a flow rate as possible. So this graph has two extremes. The shut-off head, where if you completely block off the pump, you'll have zero flow and you'll have a maximum pressure on the pump. Or the other extreme case is where you've got zero back pressure here. Effectively, you're pumping into a vacuum, an ideal closed loop where the pump is just going around on itself. You develop the maximum flow in that scenario. In a real system, it's going to be somewhere between the two, probably closer to the top there. So you'll have some restriction on the flow rate. That's the first fundamental rule of pumps and how you lay out and design your system. The second important rule with pumps and pumping systems is that the power you need to pump through something, it's non-linear, it's actually exponential. So it's very hard to get a higher flow rate through a system if it's got a lot of constrictions in it. You can't just double the amount of pumping power you need in the system. It goes up exponentially. So it's really important that you've got a low pressure drop system. You don't want to have anything that obstructs the flow of water. So what contributes to pressure drop? When it comes to the cooling system lines that you connect onto your battery pack, anything that changes the direction or the momentum of flowing water or a constriction will lead to pressure drop. So basically, if you've got a bend or a loop back in a system, the water is flowing here and then it's having to change direction. There's loss in the system when it has to change direction, and the loss is maximized when it has to turn around and come back on itself. Also, you can get pressure drop when there's a change in velocity of the flow. So if you've got a restriction in a pipe and the water has to increase speed to get through this constriction, that will also lead to pressure drop. So if you're trying to ideally lay out your cooling system, you want to make sure that the pipe you use from the pump to the battery is appropriately sized. It's the right diameter for the flow rate that's required. It also has a minimum number of bends, turns, obstructions, constrictions, valves, and many other factors, because this will lead to pressure drop, and that will lead to less flow rate that you can achieve with your system. High flow rate is really good because it means more even temperatures throughout the battery pack. Another consideration for a Xerotech battery system is that we always want to make sure that the battery is on the suction side of the pump. So what we've shown here would not be the ideal position for a battery, a Xerotech battery in a cooling system. So every component, including the hoses, has pressure drop in it. But more importantly, large components have higher pressure drop. So for example, a plate heat exchanger, which is the most common component in a heat pump thermal management system used for battery packs, often looks like a small block with coolant inlet and coolant outlet. These plate heat exchangers have very high pressure drop because it's basically an assembly of lots of alternate plates inside of a brazed plate block. And what the water is having to do is go through a very convoluted path, constantly changing directions, very narrow openings. These components have very high pressure drop. So what that means in the pump is that when it goes through this heat exchanger, the pressure here, let's use some real numbers. Let's say our pump has a shut-off head of 1 bar. It means that the pump in this case here will be developing a higher pressure somewhere along this curve. It'll have some flow rate going through it. So let's say it was at this point here and we go across, it might be 0.8 bar. That's the peak pressure the system is delivering. So on the outlet point of this pump, it has 0.8 bar. So on the inlet side of the heat exchanger, we see roughly 0.8 bar here. As it passes through the heat exchanger, the water goes through this convoluted path. It loses energy because it's being pushed through that, so you get a pressure drop. You're losing pressure on the system. The pump is having to pump it through and loses energy. So the pressure coming out might be 0.3 bar. So most of the energy of the pump is expended getting through the plate heat exchanger. And then as it reaches the battery pack, it's now going in at 0.3 bar. Because the outlet of the battery is basically on the suction side of the pump, the pressure here will be effectively 0. So this small pressure difference can develop a large flow rate across a Xerotech battery. That's very important, and you'll see that in all of the Xerotech battery data sheets, that we show the pressure characteristic curve for it. And what that will show is to develop a certain flow rate, if you want more flow, the pressure drop will be on the other axis, the y-axis. And what's unique about Xerotech batteries is the pressure drop is really low. It's very low compared to other battery packs on the market, which means that you can develop very, very high flow rates through the pack with a typical pump. It's very important for Xerotech batteries to be at the end of the cooling circuit. The battery cooling system inside of our modules is an inflatable plastic duct. While it can operate at high pressures of several bar, for long-term durability and fatigue life, we prefer it to be operating at continuous pressures that are lower than that. So you want to minimize the continuous pressure that it's exposed to. And the way to achieve this is to simply position the battery pack as the last component before the pump in your system. This is incredibly important. You must put the battery as the final component. In the loop that we've drawn here, it doesn't matter where you put any component in the loop. The flow will be constant through this loop. It's always the same flow. It could be 20 liters a minute through this loop. But by moving the components from different points, they can experience very different pressures. So this battery pack here is only experiencing a pressure of 0.3 bar on its inlet side. But if I were to move this battery from here to directly in front of the pump, it'll be seeing double that pressure, nearly triple that pressure for the exact same flow rate. That pressure doesn't matter at all for a solid block of metal like a plate heat exchanger, but it does matter for a Xerotech battery. So you always want to make sure it's on the right side of the system. The other piece for a standard system to best optimize it is to make sure all of the relevant components are in the right locations. So the ideal plumbing system configuration for a Xerotech battery is you have the battery as the final component before the pump, goes back into the pump. Your pump goes through your plate heat exchanger or whatever form of heat exchanger you're using to put heat in or out of the battery, and then it goes onwards to the battery. So you will see the battery has the minimum pressure as it's the last component. The one other component that you would typically add in here is a header tank. And a header tank just simply holds a head of water over the pump, and you always want to put this header tank on the suction side of the pump. It doesn't really matter if it's before the battery or after, but the optimum place is after the battery, just before the pump, so that it'll prime the pump, enabling you to flow through it. Sometimes these header tanks might be through flow header tanks. So it's not just a column of water onto a T on a pipe here. It might actually flow through the header tank. And this is fine too. Both systems are acceptable. By flowing through that header tank, it's much more effective at catching air and bubbles in the system. So either is acceptable. And if you want to understand how this can benefit your system, to take the extreme case, our batteries will have a maximum pressure of 1 bar. And the reason that is inside of the pack you've got the module with the ducts flowing through the system, and you've got water inside of these ducts, and it's the difference in pressure between the inside of the duct and the outside air and world. We limit that to 1 bar max. We don't like to operate at 1 bar continuous, because with plastic cooling systems, they have different types of failure modes, like creep failure. So it's not going to burst at 1 bar. In fact, it's not even going to burst at 6 bar. But if you leave it at 1 bar for 3 years, it might slowly fail to creep failure mode. But leaving it at half a bar, it might last 1,000 years. So it's a very non-linear creep failure mode fatigue. But what's important here is if you're trying to develop maximum flow rate, if you put the battery in this location, you can have your pump inlet pressure here being maybe 1.6 bar, and it pressure drops across the heat exchanger, and you've now got 1 bar here. So the battery is experiencing a maximum pressure of 1 bar. And if you were to look at the characteristic curve of our battery with flow rate, it might turn out that 1 bar can equal 200 liters a minute, whereas 0.3 bar might only be 30 liters a minute. And the difference of where you put this battery, if you put the battery here versus here, let's say we change this around now, that this is the battery. This is over our maximum pressure. This is not allowed. You can't do that. So you actually have to decrease the pressure that this can experience to 1 bar, 1.0 bar here. But the problem is that the pressure drop of the battery is very low. So the outlet of the battery is only going to be probably 0.7 bar. And how you develop flow rate here is a difference in pressure. In the original scenario here, we had a pressure difference of 1 bar across the battery. In this case here, we've only got a pressure difference of 1 minus 0.7, 0.3 bar. So now you've got a system that can only have 30 liters a minute going through it. That's an order of magnitude lower heat transfer, flow rate, temperature spread in that battery pack, with the simple difference of taking a pump and moving the 2 coolant lines from this point to here. You reduce system performance by an order of magnitude. So it's really important to get this stuff right to maximize the thermal performance of your battery system. So one final component we want to add into our system is ensuring that you don't have any overpressure events. So we always recommend that every battery cooling system has a pressure relief valve installed before the pack. So back in our original configuration here of a battery and our heat exchanger, the battery's been put in the optimum location. You always want to have a pressure relief valve set to 1 bar to the maximum immediately before the pack. So the battery will never experience a pressure greater than 1 bar. And you might wonder how this could happen. In real systems, there's a lot more complexity than just heat exchangers and a simple loop. There may be flow balancing valves, shutoff valves, isolation valves, and it's rare that your pump is only going to be able to go to 1 bar. In a real system, especially larger systems with multi-packs, this pump might be able to go to 4 bar or more. Now, we never expect to be operating up in this part of the curve. You probably expect to be operating way down here, developing high flow rate with negligible pressure drop. But what can happen is if there's a mistake, an accident, or a commissioning error somewhere in the system, we shut a valve in the wrong place. And worst case of all, we shut it after the battery pack. What's going to happen here is that no flow can develop. It's a fully constricted pipe. The flow will be stopped, the pump will be at maximum. It's going to shoot up to the shutoff head of the pump. So the system here could be up at 4 bar of pressure or whatever the shutoff head of your pump is. That's why a pressure relief valve is so important, and that's why it's very important to be careful with your valve design. The most common failures that we see in a mistake in integration is with multi-packs, especially with flow balancing valves. And we're going to talk about that next on some of the key watchouts. So we're just going to talk about the one unique case now where a lot of complexity can arise, and that's with multi-pack installations. So we've put in our ideal system with the battery pack before the pump, but things get a little bit trickier when you've got multiple packs in parallel. So we're going to go back to our original system, a pump. We're going to put in our heat exchanger. The pump flows through the heat exchanger, goes into some sort of distribution manifold. So that's basically something that joins all these packs together. And you'll notice that we've put the packs in parallel. It's better to put the packs in parallel because that means they will have the lowest pressure drop because there's more parallel paths. So every pack you put in parallel will reduce the pressure drop. So let's say, for example, the pressure drop of one pack at a particular flow rate is 400 millibar. By putting 4 in parallel, you decrease the pressure drop of this circuit to 1/4 of that. So it's decreasing half every time. So it's better to put things in parallel. If you put 2 packs in series, the pressure drop will not be halved, it will be doubled. It will now be 800 millibar at a system level across this circuit. Sometimes that can be acceptable, and we'll talk about that in a moment. So when we put these multiple packs in parallel, and it flows around to our circuit, and we put our header tank back in, one of the main watch out areas to look at here is you do want to have the packs roughly balanced. You want to make sure that all of your flow rate is not going through just one pack. In general, Xerotech battery systems have such a low pressure drop that they develop such a high flow rate that it doesn't really matter. You get very diminishing returns for excessive flow rate. But in systems where you've got any sort of throttling valves to balance the flow, and what these valves do are you're basically intentionally choking down the flow to increase the pressure drop, because the length of the pipes here will have different pressure drops for each of these paths. And you might have heard the term that water takes the path of least resistance, and that's very true. So what you're trying to do is make sure the resistance in all these cases is even. So a big watch out to do here is, especially during the commissioning phases, that you don't accidentally have your balancing valves at the back of the pack, and when you're first commissioning it, that you actually forget to open all the valves. So if these are heavily constricted, in this ideal system, you could have massive pressure drop here because they're trying to go into a choked off flow. So as you're balancing this system, you might close all the valves fully, turn on your pump, and forget that your pump is a high capacity pump because it's got to pump hundreds of liters a minute through lots of big packs here. But you shut all your valves and you didn't realize that. So now you immediately develop 4 bar or some very high pressure on the inlet side of all the packs, and you can blow every pack in the system. You've got to be very careful of that with adding any constrictions into the flow path of the battery. For more complex systems, for example, fail operational systems with parallel cooling packs that may use active solenoids that open and close these other parallel paths to isolate batteries, you have to always be very cautious of choking off the flow accidentally and developing overpressure in the pack. There's many ways to avoid that through pressure relief valves, through bypass valves and other methods as well. But the key thing here is do not ever overpressurize the pack and try and always make sure that the packs are the last component before the pump, the exception of a header tank. So they develop the minimum pressure in a real system. We'd also add that for very large scale systems, it may not be practical to put all the packs directly in fluid parallel. So for example, for very large energy storage systems, rail applications that might have 20, 30, 40 packs, it could be quite challenging to have so many parallel paths, because what will happen here is that pressure drop will be so low, it'll be very hard to develop the required flow rates through them. So sometimes you can have a parallel series arrangement that looks something like you've got maybe 3 packs in series and then many more packs in parallel. There's a lot of considerations for large-scale multi-pack plumbing applications, and we'd strongly encourage you to contact Xerotech for advice and guidance on this. There are certain considerations you want to take into account during failure modes and many other factors. If you've got one single system, all in hydraulic parallel, if you have a failure of a battery pack or a thermal event in one battery pack, it could contaminate the cooling system of the entire pack architecture. Or if you have a leak in a pack, a pipe, a valve, you could lose coolant from the entire system. So you need to decide from your system level what's acceptable, what your failure modes are, and how to make it work. And for larger scale systems, we strongly recommend putting in coolant filters in case there is contamination in the system, that you cannot compromise a large network of battery systems. So there's a lot of considerations there to watch out for. So please contact Xerotech if you're unsure about a large multi-pack installation. But for the vast majority of applications, it will just be a single pack in a loop. So the other important thing to look out for when you're commissioning a Xerotech battery is the coolant fill procedure. So within all Xerotech batteries, there are inflatable plastic ducts. This is a very unique technology that's different to all other heat exchangers in one key regard. So virtually all cooling systems in the automotive world have a standard coolant fill process. So if you've got a battery that's got a bunch of pipes of some description inside of it, you want to make sure that there's no air left in the system. And the way this is typically achieved is that you apply a vacuum to the system, basically suck all the air out of the system. For a Xerotech battery, it's really important that you pull a full vacuum on the system, a minimum of 99.9% vacuum using a proper vacuum pump. We'd recommend a pump of a minimum 12 CFM for doing this. So a standard Venturi type, airline type automotive vacuum system is not likely to be sufficient to do this type of vacuum pull down. You need to use a proper vacuum pump to pull a full vacuum down to as close to 0 bar as you possibly can in your real system. The second most important thing is that these battery modules have an inflatable duct in it. So it inflates under pressure, but under vacuum, it collapses. And that's very unique and very important, because the coolant fill procedure that works in every other EV will not work as standard with Xerotech. because when these ducts collapse in a module, this is in their open configuration, but because they're not self-supporting, the ducts are going to pinch shut. They're going to close shut like this. And when you let the system draw in the coolant into the system, it's only going to draw it in to the areas that are naturally open and self-supporting. For example, the rigid plastic headers here in the system. For you to fill up the entire system, you need to have it at a full vacuum, and then you need to, when you're driving water into the system, so for example, this would typically come out of a header tank. What will happen here is that once you release the vacuum, it's going to suck some of the coolant into the system here, because these volumes are going to stay open under vacuum, but it's not going to fill the ducts because the pressure will have equalized here. You'll have ambient air pressure up here, which is basically 1 atmosphere, and then you'll have ambient air pressure out here of 1 atmosphere. So the force going this way and the force going this way is the exact same. It will not open the duct. So instead, during the fill procedure, you need to force the coolant in. So the pressure that you're pushing the coolant in at must be greater than this air pressure. It doesn't have to be much. It can be 1.1 bar, 1.2 bar. With respect to ambient, a slight positive pressure of just a few hundred millibar above atmospheric pressure will result in the outward pressure here being 1.1 to 1.5. So you've got a net pressure here that basically overcomes the outside atmosphere, holding the ducts closed. So it'll open the duct and the coolant will flow through it. So this pressure here is different to the pressure we're describing in the system of a maximum of 1 bar, because we're talking here about the differential pressure. The difference here is actually only 0.1 bar, 0.5 bar, because it's the difference between inside and outside. So that's really important for filling coolant into the system. You must pull a strong vacuum. If you only pull to half a bar of vacuum, roughly 50% of the battery will be full of air. And that's very bad because you're only getting cooling on half of the pack, and you'll start to see errors and faults. So you must pull a strong vacuum and then force the coolant in under slight positive pressure to expand out and open the pack system. There's one other edge case to be aware of with Xerotech batteries in relation to pressure, and that relates to our maximum pressure limit. We say our batteries should have a max pressure of 1 bar flowing through the system. So one exception to this rule, or area to watch out for, is at high altitude or deep down a mine. Not many people know that when you go up high in the air, pressure will drop and the air gets thinner as you go higher. So if you're up on the top of Mount Everest, the air might only be 0.3 bar ambient air pressure. But similarly, as you go deeper, so if you're 2 miles deep in a South African gold mine, the pressure can be 1.5 bar in the outside air. So the reason this is important is if we go back to our duct cooling system, and we've got our ducts going through here, and if we have water in this duct and we start at sea level and we're just sitting here at ambient pressure, so it's effectively 0 bar gauge, it's just the standard ambient pressure. If we go high in the air, this will actually expand. So if you go up with a balloon to the top of a mountain, the balloon will get bigger. Not because you're increasing the pressure in the duct, it's because at sea level, you've got 1 bar pushing this way, 1 bar pushing this way. As you go higher, this number gets lower. It'll drop down to 0.3 bar. So actually the net pressure here is going to be at sea level, 1 minus 1, 0. It's an equilibrium. But as you go higher, it's actually going to gain 0.7 bar of differential pressure. And that's what we care about. The balloon is expanding. Similarly, if you go deep underground, the opposite happens. You could have 1.5 bar here, and you'll have a difference between the two. So you'll actually only be at you'll only be at half a bar. It's actually going to close the ducts in. It's going to try and force them a little bit shut. This happens if your system is not air vented. So if your header tank is a sealed header tank, not connected to the outside ambient air, you've got to be careful. So it's better if your system is vented because it'll always equalize pressure with the cooling system. But if it's closed loop and not open to the outside air, the worst case scenario you could have here is that if your system is closed in a loop and you're operating close to the limit of say 0.8 bar inlet pressure into that battery pack because you want very high flow rate, you're not exposed to the air. If you take this battery very high up a mountain, that pressure outside world is going to decrease. So you'll end up with 1.3 bar of differential pressure. So you're going to be expanding that balloon a lot more than you originally thought you were. And similarly, if you go very deep underground, you may actually even have to compensate the pressure because it's going to be pushing it back in. So these are outside world considerations for inflatable cooling systems that you need to be mindful of. If you have any further questions, please reach out to your Xerotech representative. Thanks for listening.